Let's jump right into this highly technical explainer, where we're going to literally adopt the compiler's perspective and trace real C code line by line. If you're a first semester BCA student studying problem-solving techniques, you are in the exact right place. We're moving past the high-level theory today. We're going under the hood to see exactly how C syntax operates mechanically.
Here is our roadmap for today's deep dive. We've got 6 core sections: getting started, variables and expressions, input and output, selection statements, control structures, and finally, pointers and arrays. Let's get right to it.
Section 1. Getting started. The minimal C program. We're going to break down the basic skeleton and see what actually happens when we hit compile.
Okay, so this beautifully illustrates our foundational logic. Every single C program you write is built from this exact same skeleton. Step 1 is our preprocessor directive, #include stdio.h. This pulls in the standard input-output library before the compiler even starts its main job. Step 2 is where the magic really starts, int main void. This is your mandatory entry point. Execution absolutely always begins here. Step 3 is where we actually do something, like outputting text using printf. And finally, step 4, return 0, is like giving a thumbs up to the operating system, signaling a completely successful run.
Moving on to Section 2, variables and expressions, memory and math. Now that we have our skeleton running, let's give the machine some actual data to work with.
C is strictly typed, which means every variable's type has to be fixed right at declaration. You can think of these types as different-sized boxes in memory. An int for whole numbers and a float for decimals typically take up 4 bytes of memory each. If you need higher precision, you grab a double, which gives you 8 bytes. And for just a single character? A char handles that in just 1 byte. You literally have to tell C the exact shape of your data before you can use it.
Let's trace how this builds into arithmetic. If variable A is 17 and B is 5, addition gives us 22, subtraction is 12, and multiplication is 85. Standard stuff, right? But watch closely when we divide. 17 divided by 5 in C does not give you 3.4. It just gives you 3. It literally chops off the decimal entirely. To get the remainder, we have to use the modulo operator, which is that percent sign. 17 modulo 5 leaves a remainder of 2. Keep modulo in mind, because it is going to be incredibly important for algorithms like reversing digits later on.
Now, you really want to watch out for this classic operator precedence trap. Look at the left side here. If you try to average the marks 78, 55, and 91 by just writing M1 plus M2 plus M3 divided by 3, C is going to perform that division first. It divides 91 by 3 to get 30, then adds that to the other marks, giving you a wildly incorrect average of 163. The right side shows us the fix. You use parentheses to force the addition to happen first, and then divide by 3.0 to ensure floating point decimal division, giving us the correct 74.66.
Section 3, input and output, communicating with the user. Let's see how we pull data in and push our results out.
So these format specifiers are basically your essential translation keys when using the printf function. C doesn't just automatically guess how to print your variables. You must explicitly use %d as a placeholder for integers, %f for floats, %c for characters, and %s for strings. When you run printf, the compiler swaps out those exact specifiers for the actual variable values you're passing to it.
But here's a crucial point. Scanf operates a bit differently than printf. Notice that little ampersand right before the marks variable? That is the address of operator. Scanf absolutely requires it. Why? Because it isn't just looking at the value of your variable. It needs to know the exact physical memory address so it can write the user's input directly into that specific location in your computer's RAM.
Section 4. Selection statements. Branching logic. Now that our data is securely in memory, our program needs to actually make decisions based on it.
And this brings us to branching logic. We use a simple if-else for basic binary choices, like pass or fail. But for multiple categories, we need an if-else-if ladder. Let's trace this for a student mark of 78. The program first checks, is 78 greater than or equal to 90? Nope, it fails the A grade check, so it drops to the next rung down. Is 78 greater than or equal to 75? Yes! It perfectly satisfies the B grade branch, prints grade B, and skips the rest of the ladder completely. Now, if we needed to check for a special award within that grade, we'd use a nested if statement for that specific distinction condition.
Now, when we're comparing a single variable against a bunch of fixed constants, a switch statement is so much cleaner than a massive if-else ladder. Here, we're converting a grade point of 3. The code jumps directly to case 3 and prints grade B. But pay close attention to that break statement. It is absolutely critical. If you forget the break, your execution will literally fall through and print grade C as well, which is a massive bug you definitely want to avoid.
Section 5. Control structures, iteration and loops. Let's explore how we repeat a block of statements without having to copy and paste our code 100 times.
Knowing when to use each loop boils down entirely to when the condition is checked and whether a minimum execution is required. You use a while loop when you don't know the exact iteration count in advance. You use a for loop when the count is known, like iterating exactly 5 times. And you use a do-while loop when you need the code to run at least once before checking the condition, which is perfect for things like menu-driven programs.
Let's actually trace a for loop in action. Executing this step by step, we initialize an accumulator called sum to 0. On each pass, we add the next element. 0 plus 42 is 42, plus 78 is 120, plus 55 is 175, plus 91 is 266. And finally, adding 63 predictably builds our exact sum of 329. The loop stops right when our known iteration count is reached.
Conversely, a while loop is ideal for something like reversing digits, simply because we don't know the exact iteration count in advance. Some numbers have 2 digits, some have 10. By repeatedly using the modulo operator to peel off the very last digit, and then using integer division to shrink the number down, the while loop neatly transforms 489 into 9084. It stops only when that shrinking number finally hits 0.
Within these loops, you have really fine-grained control. Remember that break immediately halts the innermost loop, which is perfect for a linear search. The split second you find your target, you break out to save time. Continue, on the other hand, just skips the rest of the current iteration and jumps straight to the next one. And goto. Well, goto is an unconditional jump to a label. It makes your code incredibly tangled and hard to read, so it should generally be avoided at all costs.
Section 6. Pointers and arrays. Manipulating memory. This is where we reach the foundational mechanics that unlock all those advanced array-based algorithms.
Let's see how this builds a true swap function. If you try to swap 2 variables by just passing them normally, it fails. C uses pass by value, meaning it only copies the data. It's like handing someone a photocopy. The original variables remain completely untouched. But looking at the right, passing by address using our exchange int a, int b function with pointers and the and dereference operator allows the function to reach back and modify the caller's memory directly. This is the exact exchange logic every single sorting algorithm relies on.
These constructs let us manipulate massive collections of data. 1D arrays hold our flat lists of numbers, while 2D arrays act as matrices for complex math. And to keep things organized, a struct lets us group related variables, like a student's name, their marks, and their grade, under one single roof. We can also use unions to share exact memory locations between variables, and utilize command line arguments, argc and argv, to pass data directly into our program the very moment we launch it.
Section 7. Practice exercises. Test your logic. Okay, it's time to put on your compiler hat and test your new understanding with a few final challenges. Can you trace the memory state and output for these 3 challenges without actually running them on a computer first? Try to mentally walk through the array 10, 20, 30 in a loop. Draft the precise syntax to grade a 55. Blueprint a book struct with a title and a price. Because here is the ultimate question I want to leave you with. If you can't accurately trace the logic on a piece of paper, how can you expect the compiler to understand what you want it to build? Think like the machine, and I'll see you in the next explainer.